Hello and welcome to the next seminar on discovering OpenSees, surfing the waves of OpenSees seminars. My name is Frank McKenna and today's topic is Advanced Scripting Techniques and Tips. This seminar is brought to you by the Georgie Brown Network for Earthquake Engineering Simulation NEAS through NEASCOM and the Pacific Earthquake Engineering Research Center PEER. Outline of today's seminar, basically I'm going to talk to you about programming. I'm going to introduce you to programming concepts, give an example of what I would consider a well-programmed script, and finally I'm going to talk about procedures, more on tickle procedures and what you can do with them to make you a better programmer, or to make your programs that much better. So first off, programming. So why programming? Well, basically, how do people interact with OpenSees? Basically, they write a script, they send that script to the interpreter, and they'll get their output. Each script you write is a program. To develop scripts that are easier to generate, easier to modify, debug, easier for others to decipher, and less error-prone, you simply have to write better programs. So the question is, are you a coder or a programmer? A coder, basically somebody who, given a problem, starts writing code and is eventually capable of getting that code to run. A programmer, on the other hand, is someone who actually thinks about the abstract solutions to the problem before they even open up the code editor and start writing their code. Once they have the design, then and only then do they go about implementing the design. In short, you want to be a programmer, and hopefully in this seminar today I will convince you that you want to be a programmer. But in 40 minutes I can't show you how to be a programmer. All I can do is start you down the correct path. So, on program design, how do we design our program? Well, there's two ways of constructing a software design. One is to make it so simple that there are obviously no deficiencies, and the other is to make it so complicated that there are no obvious deficiencies. The first method is far the more difficult, but it is the one you want. This is a quote from C.A. Hoare, The Emperor's Old Clothes, an ACM Turing Award winner in 1980. Another acronym a lot of people use is KISS. You've probably all heard it. Keep it simple, stupid, or keep it simple, student. Now, computers. Computer is a pretty stupid machine that stores a bunch of zeros and ones. But what it can do is it can move these zeros and ones around very, very quickly. It only deals with zeros and ones. It knows nothing about, say, files or characters or anything else. Now, what makes a computer useful is something called abstractions. Computing is all about constructing, manipulating, and reasoning about abstractions. An important prerequisite for writing good code is the ability to develop your own abstractions and to handle these abstractions you develop in a clear and precise manner in your program. Now, an abstraction, it only captures those details about an object that are relative to the current perspective. You only make the abstractions as complicated as you need to for your current situation. Now, through the process of abstraction, the programmer hides all the relevant data about the object in order to reduce the complexity and increase the efficiency of the program. Now, of course, you can take abstractions too far. When you writing code and developing your programs and planning what the abstractions are, you need to figure out what is the right level of abstraction. Initially, this will not come easy. It takes years to develop good programming techniques, and you build upon what you've done in the past. But you will get there. So, on program development, there's basically a number of steps that go through in creating a program. One, when you do it as a programmer, is to plan the program, then you implement, test it, and document the program, and then finally when it's ready you deploy and maintain it. Now there are a number of models that programmers use for going through this process. The first and oldest is the waterfall model, where the programmers, they get the requirements for the program, then they go about the design of the program, they implement that design, they verify that implementation, and finally they deployed that verified code. As I say, it's called the waterfall model. It is used commonly where the requirements are not going to change as the program is being developed. But a lot of times that is, it's not what people want. The people come to a programmer, they'll give them what they want, and then it's before they've actually got the finished product. They've actually changed. They've changed their mind, or technology has changed, and they want something different. So to allow for this sort of changing requirements, there's a number of other models that have been proposed. One's the life cycle model, and two is the agile model. The agile one being that sort of the most current programming development model that most programmers use, where at any stage in the program development, you can go back to a previous stage, or you can go back to a couple of stages previously and make changes there. For example, in the verification problem, if you're finding problems, you go back to the implementation and change the implementation. Or if the implementation was having problems, you go back to the design and figure out, well, let's come up with a better design. So when writing programs, you want to write clear code. Basically, to make your code easier to read and for others to read, you want to make it clear. Well-written programs are easier to debug, easier to maintain, and have fewer errors. It's not me saying this. This is proven in the literature. And you'll only appreciate good style when it's your task to understand and maintain someone else's code, and even debug your own code later. So, some pointers for writing clear code. One, you want to keep the programs and methods short and manageable. Use straightforward logic and flow of control. You avoid magic numbers. You want to use the language. By this I mean you want to use all the features that are available in your language. And you also want to use functions and variables. When you're using functions and variables, you want to use meaningful names that convey the purpose of the variable or procedure. You want to use names that you can pronounce. You want to be consistent, i.e. lowercase for, say, all your variables, and uppercase for the procedures, or uppercase mixed lowercase for constants. And you also want to use short names. You don't want your lines of code to look incredibly long. So keep those names short. And finally, you also want to use comments. They're available in the code. Every programming language allows you to comment the code. People just have to start using them. Some people actually suggest before you actually write the code, you actually comment the code. So you write the comments first, and then you code to what you've commented. The comments come from your design. The code explains to the computer and the programmer what is being done. The comments explain to the programmer and others why it's been done. You also want to check return values. Always check your return values from a procedure. And you want to provide useful error messages if there's errors in the code. And here's a trust example. This is the example we show in introductory to OpenSees workshops and seminars. It's the simplest example to demonstrate how OpenSees would typically work. There are no comments, there are no variables in this code. Now, if we wanted to add variables and comments to the code, the question is how do we do it? How would we make this, or how should I have done this differently to start people off correctly at the start? So I could have done this using variables. A lot of people do this, take this approach when they're developing their code these days. You go to look at the message board is typically what you'll see. They'll have their model builder, and then they have a whole list of variables. They set these variables at the start, and then they use them as they actually go through the OpenSees commands. For example, creating their nodes, they're using coordinate variables that they define. They create the elements, the materials, everything. All the commands are actually using these variables. Now these variables, people use them because they think the code is, it's easier to check validate the code, that it's, doing what they want it to do. For example, they can look at the element command and they see, well, these are how the arguments for the truss is. It's got an area 1 and a material tag 1. That's right. Then if they want to verify that A1 and mat tag is 1, then they'd come over to their variable list and have a look. Well, A1 is this, and mat tag 1 is that. So everything looks okay. So there is a problem with this. This is not the way to, check whether your code is correct or not. It works, for example, in this small example because it's, I can get everything in one sheet. But what people are doing is they've got big models. They have variables at the top, their code in the middle, and then checking, while the code might look right for the element, verifying that that A is, what if that A is correct means I'm going searching back up to the top of the file to go find that variable. So it's not conducive to clear code development, which is one of the things we're shooting for. So as I tell people, don't do this if you're doing this already. Stop doing this. There is a time and a place for variables, but it should not be used to document the code. If you want to document the code, you use comments instead. Variables are useful when you want to change a variable at some point later in the code, or you say you use mathematical expressions. Typically what you want to do, if you want to comment the code, you want to use comments instead of variables. Here's this same example with comments instead. To me, this is much easier to figure out what is going on. I can see, example, my area for trust. They're using the thing to, well, here's the area, and then you just check if that, the fourth variable in is the area. Is that the correct area? To me, this is much cleaner than setting that variable somewhere else. I encourage you strongly to take this approach to documenting the code, not the other approach. Use comments and do not use variables. Now, as I say, there are times and places when we want to use variables. Here's a simple little example, little sort of power programming technique for the power users of OpenSees. Basically, every program, when you start it, there are variables that you have access to, argv and argc. These are the command line options that you provide when you start OpenSees from the command line. You can use these argv and argc variables in your scripts to take information that you start the program with. Here's an example where I'm passing E into the program. E for the modulus of elasticity. It's coming in through the command line. Then I'm using the argv variable. It's a list. I'm using the first index. That's going to be my E. And here's an example where I'm running it. For example, this script is example2.tickle. I'm running it through OpenSees, and I'm saying that initially let's try E of 3000. If I want to run it again with E of 6000, I just do it from the command line. The advantage here is you do not have to open up the file again, change the variable, save the variable, and then run the file again. You do it all from the command line. So in the Introduction to OpenSees workshops and seminars, I also go through a slide containing pretty much most of the tickle commands you'll ever need to use. My problem is most of the commands everybody seems to be using are the ones shown here on the left. People seem to be forgetting about the ones on the right. In particular, this procedure is just not being used in the scripts that people are writing. So what I'm going to go through now is an example of what I would consider a good programming style for a particular analysis model. So the question is, how many fibers? How many fibers in a section? You don't want too many because of the cost of the computation and memory demands. And then you don't want too few because you're concerned about accuracy. Most graduate students, most scripts I see, everybody's got around 100 fibers in their sections. The record currently stands at 11,210 fibers in every section in somebody's input script. Needless to say, that program was just not running for very large models because they're running out of memory. So the question is, how many is enough? Professor Philippou wrote a paper, Section Discretization of Fiber Beam Column Elements for a Column Inelastic Response, down here on the left, in which he looked at a number of steel W sections and concrete sections. figure out how many fibers did he actually need. So he had the results of a single column test, and he was looking at how many fibers he needed. And lo and behold, he found that for a steel W section, he basically only needed 12 fibers to get an accurate response. And for column sections, concrete column, he only needed 17 fibers. Far fewer than the 100 everybody's using. So we wanted to put this to the test on a, something other than a single column. So he chose a moment frame, steel moment frame. A student at Berkeley did this. This was the moment frame we were using. Steel, all W sections fixed at the base. And the student created a script to build that model. The script used these variables that everybody was typically using to create the model. The important thing to note here is that this script to build that rather simple model had over 350 lines of code to build a very simple model. So I came along and said, okay, well let's clean this up. I do not want 350 lines of code. How many lines of code can we actually do this in if we actually program it instead of just writing the first thing that comes into our head? So again, we look at the problem. What is it? Well, it's a nice rectangular grid of steel W sections. So let's make use of that fact in our script. So what I did is let's change the column lines from A to be numbered column lines 1 through column line 6. And let's have our floors, instead of numbering them base, floor 1, floor 2, and roof, we're going to call them floor 1, floor 2, floor 3, and floor 4. Now I'm going to create nodes and I'm going to create elements. So how am I going to number my nodes and how am I going to number my elements? Well, I'm going to number my nodes for this model given the column floor location. So $column, $floor will number each node. So for example, the bottom left node, column line 1, floor 1 is going to have a node tag of 1, 1. Node there at column line 4, floor 3 will have a number of 43. Similarly, we got 24. Now how do we number the elements? Well, each element has got to have a unique number. So a unique number for each of these elements is just going to have the $I node, $J node. So for example, element 4252 there is going to go from the column line 4, floor 2 to column line 5, floor 2. That's how we're going to number that element. Again, element 5152, the same thing. It's going to go from column line 5, floor 1 to column line 5, floor 2. This, of course, for people who look at this long enough, we'll break down when we have more than 10 column lines or 10 floors, because remember, we always need a unique node tag or a unique element tag. So all you simply do is if there's more than 10 columns or floors, you start the numbering at 10. So instead of column line 1, we'd have column line 10, 11, 12, and so on. And that way you'll still get your unique column lines and node numbers and element numbers using this scheme. So, using that scheme, and also using this steel W sections.tickle file, which I'll talk to you later about, we're going to build that same exact frame that took 350 lines of code to do. So the first thing I'm going to do is I'm going to create some lists. I'm going to create a list containing the floor locations and another list containing the column line locations. Two more lists for the masses in the X and Y directions for this model. They wanted them to be different. With my lists, I'm going to then go about building my nodes. So here in 6 lines of code, I'm going to construct all my nodes, and I'm going to fix the ones at the base, floor 0 or floor 1, to be totally fixed. So this is how, it's pretty much how I do it. Basically, for each column line, for each floor, for each column line, I'm going to create a node. If the floor is located at floor 1, I'm just going to fix that node. Quite simple. After I created my nodes, then we go through and we create our materials. After I create my materials, I'm going to create 2 more list variables, one for the column sizes and one for the beam sizes. The columns, they all at between every floor, or what I call every story, they share the same W section. So my list of columns is, ones for each story. For example, the W14 by 370 on that bottom story. And all my beams, again, each floor has the same beam size along every member on that floor. So again, my beam sizes array is list is three variables long. So with my two lists and my material, I go about now constructing all my columns. I create my transformation, and then for every column line, 1 through 6, between each set of floors, between floors 1 and floor 2, I'm going to go figure out what my section is. I get that section from the column sizes list, and then I'm going to create an element for that column. I'm using a procedure that I define in the SteelW sections file. So there I've done 1, 2, 3, 4, 5, 6 lines of code, or 7 lines of code. I have added all of my column elements. Same thing for the beams. Basically I create a transformation for each column line. That's between each pair of column lines, and for each floor, 2, 3, and 4. I'm basically going to go get the section from my section list, my beam sizes list. I'm going to create an element. Again, I'm going to use a force beam W section 2T procedure that is defined in that SteelW sections particular file. And there you have it. In 35 or 36 lines of code, I have created my frame model that was taking the graduate student 350 lines of code to do. I would put it to you that this code is a lot cleaner. It's very clear and precise. It is very easy to see if you've made a mistake. You can have a look at column floor locations. Have I got the right? Are those floors at the right height? Columns at the column lines at the right locations. Have I got the right floor mass? Am I using the right steel sections for the different columns and beams? I would to me that is it's very simple code to look at and understand. I think you could show that to your professor and he goes, yes, I understand this, your model looks right. I think you could come back later and say, yeah, that looks okay. So a lot of the stuff that's hidden from view is in this SteelW sections article. So what's in this SteelW? We've got these abstractions of these elements. Where are they? They're in this SteelW sections article file. If you have a look at this file, right at the very bottom, I have an array. An array is a typical data type that allows you to store key value pairs. For the key for my array, my W section array, is the section description. For example, the W44 by 335. And then the value for that key is basically the list of all the properties of a W44 by 335. For example, the area, the depth, flange, width, flange, the IXX and the IYY. It's all there. And then, for example, if I wanted to create now an elastic beam using that array, I've got a procedure in here, an elastic beam W section 2D. Takes the elements tag, the inode, jnode, and then the section type. With that section type, it basically goes in and gets from the array the appropriate list. And from that list, it extracts the area, the I, and the IY. Once it's extracted it then can create the elastic beam column. Now the force beam and the displacement beam section procedures that I also have in this file, they're pretty similar. They go. There's a global procedure in this file, fiber steel W section 2D that, for example, will construct a fiber section given the W section. Once that fiber section is being created, it will then create the element of the appropriate type. So the results, for those of you who are interested, many of you should be, as I say, you're all using about 100 fibers, and it's way too many. For example, for this building, for the 10% and 50-year event, there was 40 earthquakes looked at. The results for the displacements and for the acceleration are shown. For displacements, you can get away with 2 fibers in the flange, 4 fibers in the web. Give you a reasonably good answer. If you're looking at the accelerations, you might want to go to the 3 fibers in the flange and 4 in the web. As I say, if you do this, you will cut down on your memory and your computation demands. For this example, for the 3 and 4 fibers, say, it took 309 seconds to do the analysis. If I'd used, say, the typical 100 fibers in everybody's model, it would have taken 1,300 seconds. So it's a savings of four times in the analysis time. Maybe it was the earthquakes were so small, you say that, well, this thing remains essentially elastic, so it really doesn't matter. So here's the 2% in 50-year event. Again, the 3 and 4 fibers is more than adequate to capture the response, even if we're looking at the accelerations. So that's the example program. A little bit of insight on how many fibers to use, just to reinforce the programming concepts and also to hopefully educate you on how many fibers you should be using. But now when you're done with the program, it's always a good idea to spend a little bit of time and critique it. It'll make you a better programmer. Well, you consider, if I was to do this again, what would I do differently? So I look at my program, this W section file, and when I was running it, I kept having to open up this file and change the number of flange and the number of web. So if I was doing it again, I would have done this differently. So what would I have done differently? Well, I'll show you. But to do something different, I have to talk a little bit about sort of what you can do with procedures in Tcl. So the basic procedure can be defined with a set of required arguments. Here's the example procedure sum that takes 2 arguments, x and y, and just simply returns the sum of x and y. If you ever had this script shown in the box, and I do that put us at the bottom, when I run this script, I would see that the sum of 3 and 4 is 7. Now, other things you can do with scripts. Well, a variable in the procedure can be defined with default values. Here's an example. For example, this procedure sum, it takes 2 arguments again. But if the second argument is not provided, it defaults to a certain value. In this case, y will default to 0. So if I again use this thing, I either pass it 1 or 2 arguments, it will work for both. And that again is what's happened. So again, we get this procedure with default values defined for our arguments. Now, much more useful feature is by declaring args as the last argument of the procedure can take a variable number of arguments. Again, here's our sum example. I'm just expanding on the last procedure definition. So this procedure sum, this args is this last variable in the input arguments. So the sum expression $x plus y will return what was there before. And then what I can do is I can loop over, args is a list, and I can loop over every argument in the list and basically add that to the sum. So again, here's using my new procedure sum. So here it can take, as I say, it can take any number of arguments. And when it's done, when you run it, you'll get that. So let's go back to steel W sections. What would I do differently? I would basically throw an args at the end of that argument list. So now I can play with what's coming in. So one thing I'm going to do is I have my defaults there. I'm setting my orientation to be XX. I'm setting the number in the flange to be 3, number in the web to be 4, and the number of integration points to be 4. So what I'm going to do is, in arguments, if, say, for example, I'm going to specify, if in arguments there is the string number of flange, the next argument will be how many fibers in the flange I'd actually want. So I'm then going to go into that arguments list and take out the number in the flange. And then, so I won't be taking my default, I'll be using whatever is passed. So here's an example of this modified command in use, where it works as is, but if I wanted to, say, change my model so that I had 5 integration points instead of whatever is in the default, I just put in number of integration points, 5, at the end of the command, and it will work. And as I say, it will work without that number for integration point 5. For example, if I'm defining my beams, didn't want 5 integration points in my beams. I could just leave that off. So other things we can do with procedures is use pointers. Here's a real simple example where I'm defining 3 procedures: eat, drink, and inhale. Each take 1 argument, and I just do a put as I'm eating $x, or drinking $x, or inhaling $x. An example of how I might use this is these next two little bits of tickle. In the first, I'm setting another array where I'm associating the word solid with eat, I'm associating the word liquid with drink, and the word gaseous with inhale. And then when I want to, invoke solid with sort of as bread as the argument, or solid as eat, I'm going to just do this $.fp. So it's just invoking the procedure on a variable name with $fp is like passing the procedure name. Now, how might we use this in our scripts? Basically, say we had a file containing a whole bunch of procedures on this, how to construct different types of element types. You could at the start of your script, you could build this mapping table in which, say, I'm going to all my column elements are going to be column force beam elements, and all my beam elements are going to be elastic elements, say. And then when your script where you're building your elements, for example, you're adding your column types, is this $LE collie type, would actually invoke the right procedure inside this other file. So what this does is that for those of you who do sort of parameter studies where what's the effect of an elastic beam or a fiber beam or displacement beam, and there's a whole bunch of if-elses in your code, you could remove all those if-elses and just put in uses passed by procedure pointer. So in conclusion, to become a programmer, you first have to design your program. You got to think about abstractions, and you got to, whatever you do, you got to keep it simple. When you're writing your code, you want to format it. You want to be consistent with the formatting. You want to use variables and procedures. Be consistent. Use meaningful names, and don't overdo it with those variables. Don't use the variables to comment the code. Do use comments. Don't overdo it though. And as I mentioned, some people suggest writing the comments before you actually write any code. You always want to check the return values, you want to provide useful error messages, and you also want to become familiar with the programming language that you're programming in, and use all the features that are available to you in that programming language. So that's my conclusion. I'll just remind you that upcoming March 27th, we have Professor Michael Scott from Oregon State University talking about reliability analysis in OpenSees. For those of you who don't know what reliability analysis is, there's a simple little tool on NISHub. Inside the OpenSees lab tool, there's this moment frame earthquake and reliability analysis. What it does is it provide a number of ground motions. In this case, I believe there's 8 ground motions. You specify what your frame is, and for every ground motion, you'll get a range of values. This range of values corresponds to what would happen if, say, the E and the Fy and the B in the different elements within this frame were all to vary some variation based on basically what's behind the LRFD. The little figures, there's a little red circle there in all the figures. Well, that's what happened if you just use the mean value. The typical E29,000 KSI, or the 29,000 FY of 50, that's kind of the mean. So the red dot shows what you'd get for your typical single deterministic analysis, and then the blue dot shows the scatter for the reliability analysis. Now, what are the possible ranges, realizing that, well, we don't know that much, we don't know the exact properties of our materials. So I encourage you all to attend on March 27th. With that, I will now go over to answering any questions that anybody might have based on what was presented today, or I know a lot of you like to sneak in questions that you've been thinking about that are related to other topics, so now is your time to ask me any questions. For those of you who are signing off, I thank you for attending, I encourage you to fill out the WUFU that'll pop up when this thing is over. And again, I encourage you to attend the seminar on March 27th. Thank you very much. So now, any questions from anybody?